Okay, let's get going. I hope you had a good break, brief break, time change and everything. So, we're in the second half of the semester. We're looking at various practical and practical implications of the tools that we've learned, looking at different kinds of filters and moving towards these specific filter design techniques to allow us to design filters with arbitrary properties to serve frequency domain, energy shaping tasks that we might have. We were just looking at a couple of special filters, which are comb filters, which just do this thing of compressing the frequency response so you get multiple repetitions of a given frequency response of a parent filter when you replace the delays with longer delays, which is like, you spread it out in time, so you squeeze it in frequency, but the periodicity of the frequency response means that when you squeeze it in, you get multiple repetitions. And then we looked at all-pass filters that have this interesting property that their gain is constant, but their phase response is not zero or linear, which would be a kind of a degenerate phase response, but something that actually does shift different frequencies by different amounts. And we found that they have this structure where they have reciprocal poles and zeros, particularly if they have real impulse responses so that all the roots occur in conjugate pairs, then you're going to have the structure where you have these sort of mirror images in the unit circle of the poles on the inside of the unit circle and zeros on the outside of the unit circle. And that comes from these mirror image polynomials, where the polynomials are the same coefficients but in different order for the numerator and denominator. And I tried to show that you can show why that works algebraically, but that's the slightly surprising construction. So the next thing I want to talk about is the idea of minimum phase in filters, and there are other concepts like maximum phase that are related. And this ties into this idea of these reciprocal roots. Now, in the all-pass system, what was happening was we had poles inside the unit circle, which, if they were presented alone, would lead to peaks in the frequency response. Right? These on the in the closed form of the Z-transform has these poles sticking up. They're inside the unit circle, but at the unit circle, they still have these slopes that would then give us peaks in the frequency response. But outside the unit circle, we have these zeros corresponding to these holes in the Z-transform surface. And then right on the unit circle, the poles and the zeros are canceling out, so the overall net response on the unit circle, the frequency response, the Fourier transform, is constant. If you scale it right, it's unity for all frequencies. And so that's because it turns out that the influence on the Z-transform of these reciprocal poles is, in that case, complementary, but in general, it's equivalent at some level. So the idea of a minimum and maximum phase filter is that you take a root in one system, you replace it with its reciprocal, meaning you just take it and move it outside the unit circle or back inside the unit circle. And that has the effect that the magnitude response remains unchanged, but the phase response is changed. And so you get several filters with identical, same order, pretty similar filters. They have identical magnitude responses, but they have different phase responses. And so, but there's only a small number of them, depending on how many zeros you can move. We could think about moving both poles and zeros, but because the process of replacing a root by its reciprocal means if it's inside the unit circle, it's got to move outside the unit circle, because the reciprocal will have a radius 1 over the radius of the original and an argument, the negative of the argument. So if we could start off with a system with poles, they're all going to be, and it's stable, then they're going to be inside the unit circle, but if we try to replace them with the reciprocal poles, they would be outside the unit circle, so they would not be stable. So we can only really do this for the zeros. But here's an example with one pole and one zero. They're both inside the unit circle to begin with, and because we've got a zero near DC and a pole somewhat near the Nyquist frequency, it has this kind of high-pass response that it tends to cut these low frequencies and boost these high frequencies. But it has this nice, well-behaved phase response. There's a little bit of phase advance for intermediate frequencies, but mostly quite close to zero. But if we take this zero and replace it by its reciprocal, So this is a real 0 on the real axis at b, z equal b, and then replace it with z equal minus b, which just means the 0 here is z minus 1 over b. Sorry, replace the 1 over b here. Then we get the same magnitude response because the 0 is having the same influence on the magnitude response. But the phase response is now different. And in fact, the phase response is less well behaved if we're shooting for a phase response close to 0, because it actually has this sort of phase that continues to experience more and more delay as frequency increases. So we could have done, if we'd had more than one 0, we could have done this for each of the zeros individually and ended up with a whole series of filters, all with the same magnitude response, but each with a different phase response. So now if someone gives you a magnitude response, and it's something that you can build out of zeros, and it doesn't already have both reciprocal zeros in it, we have various filters we could implement that would still fit that magnitude response. So we want to be able to talk about them. By convention, if there's a version where we can put all the zeros inside the unit circle, I guess we can always do that. Even if there are zeros both inside and outside a reciprocal, we could always move one of them inside and have, a double 0 at that point. So if all the zeros are inside the unit circle, we call that minimum phase, because that turns out to be the system that typically has the phase response that stays closest to 0. But if we move them all outside the unit circle, we call that the maximum phase, because that turns out to be the system that's going to have the phase that deviates furthest from 0. And then if we have some zeros inside and some zeros outside, we call that mixed phase. And obviously there's only one of these and one of these for each filter, but there can be a number of these. Because generally we don't like phase dispersion. It's like it's modifying our signal in some somewhat difficult to characterize way. It's taking a complex waveform, breaking it down to sinusoids, and then moving them by different amounts. So now the shape of the waveform, we add them back together, won't be the same. Generally speaking, we prefer the phase to stay as close to 0 as possible. And so the minimum phase filter is usually the preferred instance and the one that if nothing else is specified, that's the one you'll go for. It's normally the one that is it's most likely to show up in a simple physical system as well. That's the version that will be there if the system has zeros. Now, I introduced this by sort of saying that, it's in the same way that the reciprocal roots in an all-pass filter have a balancing effect, and if we replace zeros by the reciprocals, they have the same effect. Here's another way of linking the two, that if we have a minimum phase filter like this, with a pole, in this case 2 zeros, but inside the unit circle, we can consider taking the system, and so that would be like, putting some signal through this system, which would, cut the frequencies around here, boost the frequencies around here. We could then take that output and put it into an all-pass filter like this, that has poles exactly where these 2 zeros were, and then also, because the reciprocal structure of an all-pass filter, we'll have zeros at these reciprocal locations. Putting a signal through both of these would be the same as putting a signal through the product of these two transfer functions. The transfer functions has these roots, these zeros here, which correspond to these two terms here, and then it has these poles here at the same locations. So just by algebra, we can see that these things cancel out, which is the same as saying that if we have a Z-transform system where we have a pole and a zero in exactly the same place, then they annihilate each other. The thing pushing up and the thing pushing down are exactly in balance, so they disappear as if they weren't there at all. So we get pole zero cancellation. We end up with a system here, which is the maximum phase version of this. And so that just makes the point that, yes, the relationship between the minimum phase and the maximum phase is the magnitude responses are the same, because I was able to get one from the other by applying an all-pass filter, which doesn't change the magnitude response. But the phase responses are different, because I got one from the other by applying an all-pass filter, which will modify the phase response. And in general, it will lead to additional phase lag, phase delay, which is what we expect from the maximum phase filter. You'd think, notionally we could go the other way, but of course, if we tried to cancel these zeros and replace them with these ones, we'd have to have poles outside the unit circle, which would not be a happy thing. In ideal terms, if you had a signal that had gone through this filter, it would have no energy at these poles, and so at these pole frequencies, so it might turn out that it wouldn't actually go unstable, but numerically you'd never be able to build that exactly, so it would not be a happy situation. Okay, so that's the idea of minimum maximum phase and the moving zeros inside and out, and then also introduces us to this idea of pole zero cancellation. So now we can go back to this idea of inverse systems. If we have a situation like this, if we have some kind of forward system, and then we can design a second system such that the convolution of those two gives us a delta, that means that if we put a signal through one of these to get a modified signal and put it through the other, we get back to our original signal because the overall effect of applying both of them is just convolving with a delta, giving us identity. And so that's what we call an inverse system. We looked at that a little bit before. If we take a z-transform of both of these, now we've got this new way of analyzing what's going on here. Well, a z-transform of these is just the big H sub f of eta j omega, big H sub I of eta j omega, and the convolution becomes multiplication. The z-transform of delta is just a 1. So this is just showing that if we do that, we're going to get the output here. It's going to have to just be, in the z domain, it's going to be x of z, which means that we've got identity coming out. So this is just the idea of that we can recover, we can use this inverse system to recover the input from an output, assuming that we can construct h of I. So what's it going to be? Well, here's the relationship in the z domain, which just means that h of I is just going to be 1 over hi of z is just going to be 1 over hf of z. If hf of z is this rational polynomial, typically, that we can identify, that just means that if it's, it's got some polynomials here, then the inverse system has just got the same polynomials, but what were the polynomials for the zeros become the polynomial for the poles. What was the polynomial for the poles has become the polynomial for the zeros. And so if this was the forward system with one pole and two zeros like this, the inverse system would just replace each of the poles with zeros and each of the zeros with poles. And then what happens when we apply both of these systems in sequence is that we get the union of all these roots. But because the 0 sits right on top of the pole here, and these poles sit right on top of these zeros here, we're going to get pole zero cancellation for all the roots. And so the combined effect of applying both these systems is complete cancellation and a net effect of nothing, which is what we, an unmodified signal, which is how we designed this. So that's pretty straightforward. Right now, in this, once we've got a system defined by its z-transform system function, it's very obvious how to generate the inverse, and it's straightforward. Of course, the problem is that we can't always do this. So when we generate this, remember, the inverse is going to replace all the poles with zeros and all the zeros with poles at the same locations. So if we want to have an inverse which is, the kind of thing we can build, something that's causal and stable, then we need it to have all its poles inside the unit circle, which means that the forward system must have had all its zeros inside the unit circle, because that's where we're going to put the poles of the inverse system. So that means that hf of z must have all its zeros inside the unit circle. It has to be the minimum phase version. So it turns out of those different realizations of a simple filter with different phase characteristics, the only one we can actually invert in with a causal and stable filter is the minimum phase ones. The other ones have too much phase delay, and there's no way we can undo that without, like operating backwards in time or something, so we could use an anti-causal filter. So if we have any zeros outside the unit circle, then our inverse filter would be unstable. If we have zeros on the unit circle, then it's more obvious that we have a serious problem. We would end up with poles on the unit circle in our inverse system, which is like the boundary of stability. A pole in the unit circle means you put an impulse in, and the system will oscillate at the frequency of the pole indefinitely, because the actual sinusoid is a mode. The non-decaying sinusoid is a mode of the system. But another way of realizing this is a problem is that if we have a frequency response like this, right, if this was our forward system, this would be the frequency response of a system with a 0 on the unit circle. It means there's some frequency for which the gain is 0. That frequency is completely eliminated. If we had a signal that we put through this, and then we were trying to do the inverse to recover the original signal, well, we've lost the information about what the energy was at this particular frequency, right? It's been eliminated, it's been attenuated to 0. So just from sort of information grounds, it's clear that we can't have any real filter, any realizable filter that's going to recover that information there. Of course, you can get, arbitrarily close, and maybe exactly one frequency isn't that critical in some cases, but in general, this is the closer you get to eliminating a frequency, the more you're going to get noise problems trying to recover it, and so the more difficult it's going to be to generate an inverse. So in general, the inverse system exists only for minimum phase systems, and which also means, by extension, that means that the frequency response is non-zero for all frequencies, because if the frequency response was 0 for some frequency, that would mean you had a 0 on the unit circle, which would mean that it was not strictly minimum phase. So related to this idea of inverse systems is, inverse systems was trying to recover x given knowledge, recover the input x given knowledge of y and h. So if we have a system like this, if we knew what the output was, but we knew what the system was, we can try and design the inverse of that system to recover the input. Another problem that might arise in a situation like this is if we know what the input is, we know what the output is, but we don't know what the system is. This is called system identification. Of course, you can imagine lots of situations like that where you've got some channel, some real thing that you can feed signals in, you get signals out, but you don't know exactly what it's doing, and you'd like to try and recover what it is, or you'd like to be able to model what it is so that maybe you can go about building an inverse system for it. So maybe you know X, or maybe you just know something about X, and you still want to try and find out as much as you can about system H. If we knew X and Y, then in theory this is a system, we've got everything we need to know. We know that the system must obey this convolution sum, right? And so this gives us a lot of equations, right? For any value of n, if we know the impulse response and then the corresponding values of the input, for however long the impulse response is, then we get an equation out, and then we can repeat it for the next x and y, and then we've got a certain number of unknowns here as the impulse response we should be able to solve for. So if for instance, we had a system that was starting from rest, so we could assume that it was at 0 state at time 0, then the output at time 0 would just be the input at time 0 times the first element of the impulse response. That would give us h0. The output of time 1 would be h0 times the next input plus h1 times x0, which we already also know. So then by using our existing value of h0, we could work out h1, and we could work out going forward every point of the impulse response, because at each time step we'd see sort of one more point of the impulse response, which would basically be the first delta, the first point of x of n working through the impulse response of h of n. I mean, you can think about this different ways, but clearly if we had to find, big M values of h, then we could get big M equations out just by looking at the first M points, and then we'd have enough information to solve for those points. So this is like deconvolution, if you like. It's the inverse process of convolution. And it's clearly mathematically well defined. But notice how at every point we have to use all of our previous estimates of the points up to this one in order to recover the next point of the impulse response. And, you know, in the real world, there's always some noise. Maybe there's some noise in our measurement of y. And so it's going to be reflected in noise in each of the estimates of the impulse response, and then they're going to accumulate. So as we go on, our estimates become worse and worse. Plus, somehow this is a little bit unsatisfying in that if we want to recover m values of the impulse response, we can take the first m values of the output. But let's say we've got many, many more than that. We can observe the system for as long as we want. We'd like to be able to use that extra information, not just this limited number of points. So in particular, you know, we've sort of used 1 point to estimate h0. It would be nicer if we could figure out how to smooth out any possible noise by looking over a longer range of points. So a better approach to doing this is based on correlations. So here's our setup again. We've got an input, we've got an unknown system, we've got an output, and maybe we're not going to analyze this very rigorously, but we're worried because we think there's some noise, there's some uncertainty about what we got. Well, let's think about this in terms of correlations, and in particular, if we do the correlation between the input and the output, so Rxy as a function of the lag between the input and the output, input x and the output y. Well, correlation is just the same as convolving with one of the sequences time reversed. But from this relationship, we know that y of L is simply h of L convolved with x of L. That's the definition, the unknown h. And so y of L convolved with x of minus L is h of L convolved with x of L convolved with x of minus L. But if we gather these two together, x of L convolved with x of minus L is just the autocorrelation of x, Rx x of L. So the cross-correlation between x and y is the convolution of the impulse response and the autocorrelation of x. If we have complete control over the system, we can actually feed it a signal, input signal x, that has a particular autocorrelation structure. And then we could, again, do our deconvolution to get the unknown impulse response out. But even better than that, if we choose Rxx of L to have an autocorrelation, which is a delta, then these things would just be equivalent. This convolution would just collapse, and we just get the impulse response as the cross-correlation. Now, to have an autocorrelation of delta means that basically you've got a signal which has no linear dependence after a time shift, which is basically a white noise sequence. Or if you use you can use a deterministic sequence, which is a pseudo-random binary sequence that has exactly the minimum correlation between any pair of points up to the length of the sequence. And so in that case, you simply read off the autocorrelation with the cross-correlation, and you've got the impulse response. And this is actually, and the nice thing about this is this cross-correlation, of course, can be based on as many points as you like. It's the sum of x of n times y of n minus L, whichever way around it is. But you can sum over as many points as you have, and so now if you've got 1 second, you can sum over all those points. If you've got 10 seconds, you can average over 10 times as many points, and the noise, which is presumably not correlated with h, will tend to disappear, and you can get more accurate measurements. So this is actually how they measure impulse responses of things like concert halls. They'll go in with a speaker, play a white noise sequence, record it, and then do the cross-correlation to recover the impulse response. Yeah?
Can you explain again about noise component and output?
Yeah, what I mean about this noise thing? Well, if there was, we don't deal with any kind of stochastic stuff in this class, so I haven't put down the math. But it's very simple that if we had y of n plus, some noise sequence, v of n, then if we did the cross-correlation between x of n and y of n, we'd expect there to be a lot of correlation between x of n and y of n because, y of n is the convolution of x of n with the impulse response. We'd also have the correlation between x of n and V of n. But if V of n was just some independent noise, then if it was zero mean, we'd expect that convolution have an expected value of 0, and so it would disappear the longer we took. I mean, there would be some variance associated with it, but it would die away as 1 over n, and so it's sort of, you know, it's because the measurement noise is not correlated with the input, then the longer the window over which you calculate your correlations, right? So the correlation, if we only calculate, you know, if we just want to carry out the correlation for one lag, it's just the inner product between y and x shifted by 1 point, but for as long as the sequences we want. So the number of lags we calculate for our cross correlation is independent of how long a sample of the two signals we use. But the longer the sample is, then the more accurately we're going to measure those two, because the noise will wash out, basically. You know, you should, if you take random signals and noise, I think, which is often next semester, you'll deal with this stuff much more rigorously. Yeah.
So isn't that the case with the normal correlation as well? Like suppose if we take large number of samples,
Yeah.
and then try to recalculate using the recalculate using the convolution of x of n and y of n.
Yeah. You mean like on the previous slide?
Yeah, the previous slide. So
Well,
in this case, we wouldn't be able to.
the process I described here, we get one shot to calculate h of 0. We don't then go back and re-estimate it. Now, you know, you see. I mean, this is not a very smart process, but it is. If there were no noise, it would be fine. It would give you the right answer. But if this is actually, if y of 0 is actually just, you know, an estimate, so it's got some nu of 0 term in, suddenly that's going to really corrupt our h of 0 term, and we never recover that. Yeah.
Could we get any better results if we work in the transform domain?
Could we get better results if we work in the transform domain?
Things are in a time domain somehow.
Right.
So what about frequencies?
These obviously, these operations have exact transform domain equivalence, which is, you know, would be another way to do it. So rather than calculating your actual time domain correlation using the correlation equation, we could simply take the Fourier transforms of these things and then multiply one by its conjugate, which is the same as the time reversal in the time domain, and we get the same answer. I think. Just hold on for a second. We'll see some of that. Yes, for instance, on this slide. So, you know, what we know about the Z transform. Well, here we're saying that we've got the cross correlation is the convolution of the unknown transfer function in the order correlation. So we take the Z transform of that. We've just got the Z transform of a correlation is this power spectral density. The Z transform of the order correlation is the you know, the pure real power spectral density of X, and this is the cross power spectral density of X and Y, which shows both the total energy and the phase change between them. And so again, we've just got now the convolution becomes a multiplication. So now if we can calculate this, the cross correlation, then we know that's going to be equal to this. And so if we know this, we can divide through at every frequency, say, to get the overall frequency response of the unknown system. Now, there may be situations where, in order to calculate this, we need to know exactly X and Y, right? We need to know the precise form of those. But there may be situations where all we've got is the output of the system, and we weren't able to capture the corresponding input, so we can't directly apply this. But we may know something about the general properties of the input. We may know that it has, you know, taken over a long time, it has an order correlation structure that's stable. This is a very common situation for a signal, which basically means we know its average spectrum. We know on average how much energy it has at different frequencies, but a particular sample will have some variation in those energies and some unknown phase relationship. But if we look over long enough, then we know that the total energy is going to average out. This works for any kind of signal, like speech, for instance. If you take a minute's worth of speech, then its autocorrelation structure is fairly stationary. So in that case, if we don't know x, so we can't calculate the cross correlation. We've observed y, so we can calculate the autocorrelation of y, or its power spectral density, which would be obviously just the spectrum of y times its complex conjugate. Y is just h multiplied by x, so y times y conjugate is h times x times h conjugate times x conjugate. If we gather the two x terms, we get the autocorrelation of x, and then the two h terms give us the magnitude squared of the transfer function of h. So if we just had a y, but we knew what the autocorrelation of x was going to be, assuming we had a long enough window that we could assume that correctly, then just by looking at y, we could figure out the magnitude response of the system, even though we couldn't figure out its phase response. What that's saying is, if we know that on average x has a certain amount of energy at a certain frequency, but our output has a different amount of energy at that frequency, then obviously the system must have had a gain corresponding to the difference between those energies averaged over time. So even without knowing the particular input, we can get the magnitude response of the system. And then if we make some assumption, like, for instance, that the system is minimum phase, we can find a filter, the closest minimum phase filter of a given order that has this particular magnitude response. And so we can use that to estimate our filter. And then if we know something about how that system was built, maybe we can be sure that it's going to be minimum phase. It's just got a few poles and zeros, and so we will be able to identify the system even in that circumstance. So, obviously it depends on the domain what kind of assumptions you can make, but even with relatively little information, you can get useful results out. Okay, any questions about that stuff? All right, so now for the rest of this lecture, we're sort of changing topics a bit. And we're going to talk about the actual structures you use to implement some of these filters. This stuff, it doesn't exactly fit into the flow, but we should talk about it at some point, and so now is that point. And it's important to have this in mind before we start, trying to design these filters that we're going to be able to implement. So basically, we have a filter, we have a system which we can describe by its z-transform, by its transfer function, which we sort of know that, if someone gives us a block diagram, we can figure out what the equivalent transfer function is. And so if someone gives us a transfer function, we can probably go back and come up with a block diagram. But also we know that algebraically there are various ways of expressing that transfer function. And so we may suspect there are various ways of implementing the block diagram that are equivalent, and indeed that's the case. And so then it's like, well, there are going to be sort of second-order factors. All these different implementations, these realizations, will all have the same theoretical transfer function, but they may have different second-order properties, like the computational cost based on, the different expense of these different operations, adding, multiplying, delays. They may have different, layout properties if we're trying to build something in hardware. We have different noise performance depending on exactly where, because we're always introducing noise due to the quantization of these representation of these values in fixed size things, and so that can be important. And there may be sort of higher order factors that if we're building a more complex system, then a different factorization or a different representation of a particular part may allow us to optimize different things. So that's basically what we're trying to think about and talk about in this section. And the tool we're going to use is the block diagram, but now we're going to try and think about what differences in how we draw these block diagrams, how they relate to how they correspond to different implementations of the same system. So we looked at these right at the beginning of the class, right? We had this idea that if we have, flow graphs like this, then they correspond to, they give us a description of how a system is processed. And then we've now recognized that we can have blocks in here which are not simple delays, but are actually just complete functions. And they sort of operate very much like gains in that just as the single delay, which is z to the minus 1, corresponded in the z-domain to multiplying the input by z to the minus 1. If we have a whole system in here, in the z-domain, that just corresponds to multiplying the input by that system. And so in a system, in an example like this, we can say, okay, we've got this output y comes from g of g1 applied to this summation here. The summation is x plus g2. So in the z-domain, we can simply g2 times the output y. We can simply write down that multiplication, right? Everything becomes very simple. The delays have been folded into the multiplication, so it all just becomes straightforward, familiar algebra. Of course, here we've got y on both sides, so to get the transfer function y as in terms of x, y is the ratio of y to x, then we have to rearrange it to get the y's onto one side, but that's just straight algebra. Then we divide through by the factor that we're multiplying y by and divide both sides by x. So we get y divided by x, which is what you multiply x by to get y. So here's the transfer function in terms of these gains. And this is the familiar feedback 1 minus loop gain denominator situation. In general, we can actually solve these equations, these things algebraically, fairly mechanically. All we have to do is to find each summation node, give a dummy variable name to the output of that summation node, and then just do algebra, just eliminate the dummy variables. Here's a slightly more complex example. This is actually an important structure. This is a so-called lattice filter. And although this system only has 2 delays, so we know it's going to be no more than a second-order system, it turns out you can stack these. So you can take another one of these and connect it in here, and then you can build up higher-order systems out of these individual blocks. But they're fairly complicated little structures here, and they're built this way because this allows you to have simple checks on the parameters to check that your systems are going to be stable. But let's just see how we analyze it. I'm not going to go through this in too much detail, but basically we've got 4 summation nodes here. The output of the final one is just y, but the output of the other 3 don't have names, so we give them names, just w1, w2, w3. Then w1 is x minus alpha z to the minus 1 w3, right? So that's our first equation. These are all w1 of z, but we don't have to write that down. It's implicit now in the, that's how we're describing all of our values. w2, just look at the inputs of the summation. Okay, well, there's w1 here, and then there's minus d z to the minus 1 w2. Okay, so it's fine. It appears on both sides, but we've still got algebra to come. w3 is just epsilon times w2 plus z to the minus 1 times w2. So here it is. So now we've got our basic equations. Then we've also got y as gamma z to the minus 1 w3 plus beta w1 here. So now we can start doing algebra to eliminate the variables. So we can, we can rearrange this equation to get w2 on one side. So we get w2 as a function w1. And then we can substitute in for w2 in this equation. So we get w3 in terms of w1. And then we can substitute that into here to get y in terms of w1. We can rearrange these two to get w1 in terms of x, and eventually we get the whole thing coming out here. So we eliminate all the variables. We get our relationship between y and x. And what it comes down to is that these are just, these are simple second-order polynomials. So it's 2 poles and 2 zeros. By controlling these parameters, we can, get an arbitrary set of parameters here. So we get arbitrary poles and zeros. But the nice thing here is that these things, which are r squared, are directly observable parameters here, gamma and alpha. And as long as we make these things smaller than 1, then r squared is going to be smaller than 1, which means that the radius will be inside the inner circle, so we can control the, well, in particular, the radius of the poles. We can control that just by making sure that alpha is smaller than 1. So, you know, that's incidental.
Sorry, can you say it again?
So, I mean, just like this is why did we even introduce this structure at all? One of the nice things about the structure is that the reason that this structure shows up is because it's relatively easy to implement. You know, it's just some delays with some gains, but it's easy to guarantee that the poles remain stable. In the second order system, we can, if we keep alpha smaller than 1, then if you remember the actual poles of a system, the poles of the second order system are just, you know, it's 1 minus 2r cos theta is equal to minus 1 plus r squared is equal to minus 2. So alpha is equal to r squared. So if we keep magnitude of alpha smaller than 1, then magnitude of r will have to be smaller than 1, which means that our poles will be stable. That's also true of a direct form, you know, just the normal form. But when we get to higher order, that still remains true. In a higher order system, if you've just got the fully written out polynomial, it's hard to see what the magnitude of the individual poles are going to be. But here we have these things separated out, and so we can guarantee that all the poles are stable. That's where I've seen it used, that if you use a lattice filter, because it's, you can make sure that you don't accidentally end up with a filter with some unstable poles in it. But, you know, that's not been explained. I'm just saying that's where you may come across it. It's got some nice properties in terms of stability and implementation. Okay, so one thing that comes up in these block diagrams is that we can draw a block diagram like this, which looks kind of well behaved. It looks, you know, it looks syntactically correct. But it turns out that it is a problem because it doesn't have any delay in the loop here. It's got a loop in the middle here with no delay in it. Algebraically, we can analyze what's going on. So y is just b times this summation, which is v plus a times u. Right? So we've got this thing is called u here. U is simply x plus y. So we can write down an equation for, so you know, the inputs here are v and x, and the outputs are u and y. We can write down an expression for y here. But now, if we actually try and run this, if we think about trying to build the system, we'd set up x and v at a particular time, and then we try and calculate the outputs here. But to calculate the output for y, we'd need to know the output for x, but the output for x depends on the output for u, but the output for u depends on the output y, and so we'd end up with this recursion at time 0. You know, we wouldn't actually be able to calculate it using this structure, because we'd calculate this once, and then it would be like, oh, we need to update it and stuff like that. So that's what happens if you build a structure like this with no delay in a loop. It's something that, you know, if you actually implemented it like this, you'd end up with this unstable self-referential calculation.
Would it help if we give some initial values to each node?
Can we give initial values to nodes? Well, that would be like if there was a delay in there, then we'd have to specify what the initial value was, and then we'd be able to do it. But that would be essentially inserting a delay in here, because it's saying, well, at time 0, this is what value it has. But here we're saying, no, at time 0, the output of y is, you know, b times v plus a times x plus y. And so it's y0 is equal to b times v0 plus a times x0 times y0. Now, you know, it's not, in algebraic terms, like, well, that's not a big deal. I can just do this rearrangement. So I just expand this out, find that y is equal to something plus bay. So I just subtracted it on the other side. I get this algebraically valid expression, I can now calculate this, and now I get an expression for y that is only in terms of v and x, the actual inputs. And I can do the same thing for u. But this is actually how, if this was the system I was trying to implement, this is how I could actually implement it here. So here I've got my relationship between y as a function of v and x. So y is x times BA on 1 minus BA, this link down here, plus BV on 1 minus BA. So here's V coming in, here's my B on 1 minus BA. But now you see we have a structure where there's no loop in here. We have the two inputs coming in, they split, they branch to the two summation nodes, and then they sum to give us outputs. Whereas here we had this loop going all the way around. Here there's no loop because these things are both flowing that way. But we have algebraically, we have the dependence of x and y, of y on x and u, and x and v, and u on x and v. That's the same as suggested by this structure. It's not clear how you would end up with a structure like this, but it might be like you're thinking about something, you're trying to achieve something, and you end up with a structure like this. To realize it, you then have to go back to the algebra and then come up with a form like this that doesn't involve any delay-free loops. It doesn't come up very often, but just it's important that you understand that there are things you can write down that look okay but actually don't make sense. In passing, we know that there are these 1 minus B8 terms on each of these gains here. If B or A is a system, then these are not just gains, these will be systems themselves. And we might think that there would be a more efficient way of representing that denominator term. So that brings us on to this idea of refactoring of these systems using some of the identities of convolution. So, for instance, we know that convolution is commutative. It doesn't matter which order you apply your convolutions in. If you have a system A followed by system B, you get the same output as if you first applied system B and then system A. And so that's saying if we have a block diagram situation like this, where we have a signal going into A and then into B, that to first order is going to give you the same output as B followed by A. Not a big deal. They're both the same cost. But there may be some second order influence that makes one of those preferable. They're not going to, in particular, the value in the middle here will not be the same, right? We'll have different intermediate values. Maybe we worry about clipping or some kind of numerical problem on that value. We know that convolution is distributed over addition, which just means that multiplication is distributive over addition in the Z-transform domain. So if we have something like this, where we have the sum of two systems with a common factor, we can take out that common factor and just apply it to the sum. And so that is, if the system function was AB plus CB, that would be like, well, maybe it's AB times x1 plus CB times x2. Then it might be a structure like this, where we have, the AB system and the CB system, and then we sum them together to give y. This would be saying, well, it's A times x1 plus C times x2, then the whole thing processed by B. And this would be the factorization here, where we take, this A times B is like A followed by B up here. Then we take this B term that we applied to both of them, and we just move it until after the sum. And so then, we only have to calculate it once rather than calculating it twice. And so actually this would typically involve a small amount of computation. Although it might be that, that for some reason the limiting factor was how many times we actually had to go in and apply a system, in which case here we only have to have two processing blocks and then just a simple summation, whereas here we have to have a third processing block following the summation. Again, totally depends on the substrate that you're using to implement this, whether that would be an issue or not. In software, it typically wouldn't be an issue. There's one kind of trick which we're just going to take as a given, which is called transposition. And it's an operation you can perform on a flow graph that generates a new flow graph that has the same characteristics. And the process is you reverse all the paths. So instead of the signal going from left to right, now you make the signal go from right to left. In order for that to make sense, you have to take all the summation things in this one and turn them into just splitter nodes, and all the splitter nodes in this one and turn them into summations, because basically when the signals flow in the opposite direction, then these things become points where several signals meet, so we sum them up. And then now you've got the output becomes the input, and the input becomes the output. So this is a different structure you can see. Right here, if we sort of follow through what it's saying we do, it's saying we take X, we delay it by a couple of steps, and then we take each of those delayed versions, multiply them by different gain constants, and sum up the result. This system here says we take the input X, we immediately multiply it by the 3 gains, and then we feed these into this sort of accumulation forward delay line that we set one in here, and then we add that into the previous delayed output of this, then we take that partial sum and add it up here. So these are not just drawn differently, but they're actually different. They correspond to different sequences of operations, different implementations, but they do actually have the same effect. And in general, for any flow graph, if you do this, you'll get an equivalent system by this transpose operation. We can easily see for this case that the systems are the same just by, here's what we got for the first one, which is just B1 plus B2 times the delayed version of X plus B3 times the twice delayed version of X. And then what this one is saying is, well, this one down here is the output of the summation is B1 times X plus a delay times B2 times X plus a delayed version of B3X. But if you multiply it through, you get the same Z-transform relation, but it's describing a different sequence of operations to obtain it. So that's something you can do. So if we're now thinking specifically about FIR filters, which are these filters where we have a finite impulse response, so basically if we just have a finite number of delays, then we can write out the impulse response as gain factors on the outputs of each of these delays. So, very literally, if we put an impulse in here, then what's going to happen for each time step is that the first at time 0 it'll be here, at time 1 it'll be here, time 2 it'll be here, time 3, time 4, and then it'll disappear. And then the output is just going to be, well, the first point of the impulse response is going to be whatever this gain factor is here. The second point, h of 1, is going to be this gain here, etc. So we can build an FIR filter just by having this delay line with these taps coming off at every point, and then a gain factor, which is just the corresponding point to the impulse response. So this is called a tap delay line. It's a very natural way. It's the same as our moving average filter. Like in our moving average filter, we had these delays going down, these gains coming off. Here I've just drawn it so that the actual delay line is moving left to right. We can apply our transpose operation to this, and we get a different structure here, which is basically the same one as we looked at in the previous slide. But here, instead, when we flip this all around, we end up with these gain factors showing up as something when we get a new value of X in, we immediately apply all the gain factors to it, and then we feed them into this sort of this accumulation delay line. So at every point, we have the output from the previous thing, and then we sum in a bit more with one less delay going forward until we get the output. And it's by the properties of the transpose transformation, it's going to give us the same system as output. One situation where this might be preferable to this is if we have several inputs, each of them being filtered by a different filter, but being summed up to give a single output. here we could have a second input with a second set of H's all feeding into the same summation nodes. And then we could just use a single delay line here rather than having to have delay lines for each of our separate inputs, which of course, they're different values, so they would have to be distinct. So that's one situation where we might be able to save on our memory utilization by switching to a transpose structure. One thing that we sort of know we can do with Z transforms, Z polynomials, is factor them. And so, for instance, if we have a direct expression of an impulse response in terms of its Z polynomial here, well, this is just a 4-point FIR. It's the Z transform of a 4-point sequence written out directly. But it's also a third order polynomial in Z to the -1, which means we can factor it as a set of 3 roots. If the impulse response is real, then we know that the factors, if the zeros are complex, they're going to have to occur in complex conjugate pairs. Although if they're real, they can occur individually. But so, for instance, let's assume we have this as a single real root and a pair of complex conjugate zeros. Then we could express it like this, which would be like first filtering with a single zero here, then filtering with another zero, in this case complex, and then with another zero, which is the conjugate of that. That wouldn't be so great, because then we'd actually have to have complex coefficients in here. But if we combine these two together to get a single second-order system like this, then we know that these second-order term coefficients are going to be real if the overall system response is real. And so that factorization, which is just a way of writing that down in terms of its roots, corresponds to this implementation. Rather than having a single 3-step delay line with different gain coefficients coming out, we have the cascade of 2 systems, one with a single zero, given by our zeta 0, and then a second with 2 delay lines, 2 coefficients to give us the second pair of zeros.
Trivia question.
Yeah.
So H of Z as a polynomial, and then the next step is the factored one.
Yes.
You won't get the H of Z back if you multiply that through.
Yeah, absolutely. So that's all. I mean, all I'm saying here is that this is just written out as a polynomial. Here I've rewritten the polynomial in terms of its roots. So if I've written in terms of these zetas without defining what they are. But the point about these zetas is, when you multiply this polynomial out, you get these h's out. So it's the solution to that third-order polynomial. Because that's the critical thing here. We're saying, well, there is just one z function, but we can describe it in different ways.
Okay.
And so here we're just describing it as the unfactored polynomial sum of terms, and here we're describing it as a product of terms, which are the roots. And then here we further recombine 2 of these. So sort of, it's like we've done polynomial long division here. We've just taken this one root out here, and then it turns out this, works out nicely. But this factorization, the product of a set of terms in the Z transform, is the same as saying, well, if we're multiplying the Z transform, that means we're convolving in the time domain. And if we're convolving things successfully, it just means putting it through a sequence of systems. So here, the H0 becomes a gain here of H0. The first 0 becomes a single first-order term like this. And then this second-order system becomes this nice second-order structure here with just real coefficients. Right, we could have had 3 terms here, but then we would have had to start using complex representations for these values. Here, because the coefficients are all real and assuming the input is all real, we never actually have to worry about tracking the imaginary parts of these values, which typically we wouldn't want to get into. Yeah?
How is this better than the simple 3-tap?
How is it better? It's not better, but it's different, and there may be reasons why. you want it to be different. So, for instance, it might be you actually want to be able to vary this root without varying these ones. If you do it in this sense, then if you vary zeta 0, then all the coefficients change. But here, now we factored out, we could keep these, if these two zeros are always at the fixed point, but we're just varying the real 0, then, you know, that it makes this now is exposed in terms of the structure of the system. And so it's, you know, you might be able to, might serve you to manipulate it like that. Or similarly with these two. But other ways that might make it worthwhile is if this factor was somehow common, so we could use it. We had several systems which all had this factor or this factor, and then we could, you know, pull it out as a common term and apply it once rather than having to do it multiple times. A couple of lectures ago, we talked about linear phase FIR filters is a very important class of filters we can build that have very nice phase characteristics. And the constraint here is that they're symmetric in time. So we have a set of coefficients, which we have pairs of coefficients that are equal. And so that leads to a structure like this, where it's like, well, the first and last coefficients are the same. So rather than having a long tap delay line with two equal multipliers, one at each end, we can have the delay line, but then sum up the terms that have the corresponding gain values applied to them, and then just apply it once. And so here we can half or nearly half the number of multipliers we have to use, as well as sort of intrinsically representing the symmetry of the impulse response. So we have this sort of folded delay line here, so that points that are equally far from the center point are automatically have the same impulse response coefficient applied to them. And then once we've got a structure like this, we can always generate its transpose form, where this is essentially our delay line with taps coming off with gains. The transpose form would be, you know, the input coming in here. We immediately apply these gains, and then we have this one of these multiply and accumulator delay lines for the output. For IIR filters, we're going to have both pole zeros and poles. We're going to have a h of z, which has a numerator and a denominator. Of course, we can get a system like this as the product of the numerator coefficient, p of z, and a product of the, you know, just the denominator term as a polynomial here, 1 over d of z. And so that means here is our p of z, which is, you know, for instance, we can implement as a delay line with a set of coefficients coming out. And our denominator, which we know corresponds to feedback like this, where if the polynomial is like this with plus d1 and plus d2, it actually means delaying it by different amounts and then having the negative of these, because when we do the y of n in terms of previous y's, then we have to take them over to the other side so the signs flip. So that's, you know, our most natural, direct implementation of this filter. But again, it's got two factors now, the zeros part and the poles part. So this structure, specifically for a second order filter, so a filter with up to 2 poles and 2 zeros, is called direct form 1, and that kind of polynomial is represented by 5 coefficients, and here they are, the 5 coefficients of the LCCDE directly represented. Now, if we have these two things, by commutativity, we can just apply them. We can break it in the middle and apply them in a different order. So then we have the pole part here, followed by the zero part, but that's going to give you the same effect because it's just the product of those two transfer functions. But now we end up with these delay lines which are delaying the same values, the intermediate values, and so we just have to have a single delay line in here delaying these intermediate values, the values after the poles but before the zeros are applied, which means that we end up with less memory. And so this is called a canonical realization because it uses just as many memory elements as there are as the order of the system, the greater of the number of poles, the number of zeros, which is the minimum number of memory elements we can use. This is non-canonical because it uses more memory elements than the order of the system. And this structure is, it's got the same coefficients, just in a slightly different order. It's called a direct form 2 or DF2. It's a very common structure to implement these systems. And of course, once we've got a structure like that, we can apply transposition to that to give us our direct form 2 transpose, which again, it's sort of compared to the direct form 2, it has the zero coefficients first. So we apply these p's, then we have this, cumulative upward traversing delay line, and then here we have the poles coming in, feeding back like that. So this is also a common structure used. That's why it has this special name, DF2 transpose. We're particularly interested in implementations of just second-order systems because, of course, we can build up a system at arbitrary order by cascading multiple second-order systems. And so that's this same idea as we had in the, factoring the FIR filter, the all-zero filter, into a set of terms. We can do the same with IIR filters as well. And in particular, if we have systems which may have complex poles, if the overall system has got a real valued impulse response, then we'll always have the poles with their conjugates, and so we'll always be able to group them into pairs such that we end up with pure real valued coefficients coming out. So in this case, I've characterized the pole in terms of their real and imaginary parts, which gives us these, this would be the actual coefficients here. If I could have parameterized them in terms of r and theta, we would have got also, this would have been 2r cos theta, and this would have been r squared. Of course, we may have some real roots as well, but they're not. They can also be, if we have more than one real root, we can combine them to give us a second-order system which also still has real coefficients. So if we have some arbitrary higher-order IIR system with both poles and zeros, we can factor it into a series of second-order systems taking conjugate pairs of the zeros and the poles, combine them together to give us real valued second-order sections, and then we can just pass the signal through each of these to give us our overall system. We may have, if we've got an odd number of total roots, we may have one first-order system, which of course is just a second-order system with the bottom two coefficients set to 0, and then we can add in as many of these second-order stages as we need to get up to cover all the poles and zeros that we have. Interestingly, in general, a second-order system has 5 coefficients, 2 feedback and 3 feed forward. But the feed forward coefficients in the sort of the top row are simply gains, and so we can commute all of those back to a single gain at the beginning, and then we just have these 4 coefficient second-order systems, which we can, because we can always represent a system in terms of these, we can spend a lot of effort into optimizing this structure. And then we don't have to have a separate optimization for a 4th order or a 5th order system. We just say, okay, we're going to optimize a second order structure, and then we're going to reuse it with the appropriate factorization. Oftentimes some of the factors some of the secondary considerations which will differ between these different realizations correspond to how we represent these coefficients. The effects of quantization and how many bits we have to use to store them, or how many bits we have to use to implement these multipliers. And so that can be something that you can also try and control when you've got a single system, a single simple structure you're looking at. When we're decomposing an arbitrary system into second-order sections, we have a number of choices, different ways we could do it. We have to group together the poles and zeros with their conjugates. But in each second order section, we're going to have one pair of poles and one pair of zeros. And we can group those, we can arrange those however we want. It's going to give us the same result. And of course, if we end up with some number of second order sections, we can apply them in any order. They're still going to give us the same result. So then it's like, well, how do we choose between these? And now we're going to look at these secondary considerations, basically the numerical properties. And in particular, we'd like to keep all the intermediate values of about the same magnitude as the input and output to the best of our ability. Because if we have intermediate values which get very large, we can end up with hitting some numerical limit. We can get overflow, particularly in fixed point implementations, which were generally simpler than floating point implementations. And similarly, if we have very small values, we can start hitting the quantization limit of our representation. So MATLAB provides a function ZP2SOS, which takes zeros and poles and converts them to a representation in terms of several second-order sections. And it not only figures out the roots and converts them to second-order sections, but it also structures them to try and optimize these considerations. So for instance, if you have a system like this where we've got 4 poles and 4 zeros, and in the overall system, they're in these close pairs. And if we remember, if we have a pole and a zero close together, then for frequencies far from the pole and the zero, they sort of cancel out. They have a local effect that only for the frequencies around here is there a significant difference in the relative position of the pole and the zero. If the pole is closer, then it'll be a peak. If the zero is closer, then it'll be a local notch in the frequency response. So here we see there's first a little peak corresponding from this pole, which is for distant frequencies compensated by the zero, and there's a little notch here from the zero, which is otherwise compensated by this pole. So there are 2 ways we could arrange the poles and the zeros. We could have the poles and zeros that are far apart, or we could have the poles and zeros that are close together. If we have the poles and zeros that are far apart, basically we start off with a system that boosts the frequencies, the low frequencies, a lot, cuts the high frequencies, and then we have sort of a complementary filter that cuts the low frequencies and boosts the high frequencies. When we combine these two, we get the overall response with the small kinks. But in between, we had values that, for instance, here the peak gain is like maybe 6 dB, but here we've got a peak gain of up to 20 dB. So if we had some value coming in this frequency, if we put it through the whole system, it doesn't get amplified by very much. But here it's going to be amplified by maybe 10 times more. And so if we were close to clipping, then we'd end up with the system giving us clipping. By contrast, here we have the nearby poles and zeros stay grouped together, and so the output after this first stage still only has this small gain applied to this frequency. So in general, this is the preferred factorization, where you try and keep the pole pairs and zero pairs paired, so they're the ones that are closest together, the ones that have the greatest mutual compensation effect, so the intermediate results have the smallest maximum gain excursions. Okay, so finally, another thing we know we can do with z-transforms is we can take polynomials and write them in terms of sums. This is what we did to do the inverse z-transform when we used the partial fraction expansion. So if we have some h of z, we know we've actually got a technique to expand it as the sum of a set of individual poles. We could also do that. I mean, these poles in general will be complex, but we can group the conjugate pairs, so we could make it as a sum of second-order poles, which now will typically have first-order FIR numerators, single zero numerators. Summing things up in the z-domain just means summing their results in the time domain. And so that suggests a structure like this, where each of these individual second-order partial fraction terms becomes a system like this with two feedbacks and then just a single first-order feed forward. But then we take each of these, we feed the input into each of these, and then we sum up their outputs. And this is actually different. This is still this is kind of like a factorization in that we're breaking it into multiple terms. But rather than applying them each in sequence, we're applying them all in parallel, which, and they're different systems that we get out. Actually, the poles are the same poles because that's how it works, that if you have something where the system explodes, it's going to explode whether you do it in a sequence or in parallel. But the zeros are different. And so there are a couple of advantages to this. It actually, if you've got some kind of propagation delay thing going on, then having all these things calculated in parallel can be, can let you calculate the result more quickly than having to wait for one stage to be finished before you can calculate the next stage. And then there may be reasons why these particular arrangements of zeros are easier for you to deal with than the other ones. So this is just another, depends on the situation, but something else you can try and do. Okay, that's it. Any questions about that? All right, great. So I'll see you on Monday, and we'll start talking about some other filter design processes. And the homework is collected today, please.